So now let's mix the idea of work and ideal gases. So imagine that we have the system, we have a gas inside this piston. There is this movable wall here, and we know the gas has a pressure, and that pressure, so therefore there's going to be a force on this piston here, and there must be an external force that keeps the piston in place. Otherwise, it would fly away, right? So, and we can write that the we can write that the external force is equal to minus the force of the gas, right? They have to be equal and opposite to keep the piston in place, this wall in place, right? So imagine that now the wall moves a little bit and very slowly, so the two forces are always almost equal, right? So it moves the distance dx. So what is the work done by this force during that motion from here to here? Well, the work done is equal to the external force times the x, which is also equal to minus the force from the gas times the x, right? Because of this relationship. Now, remember that the pressure from the gas is equal to what? Is equal to force divided by area, right? So therefore, we can write that the work done is equal to minus the force of the gas, and this is minus the pressure from the gas times the area from this relationship, right? Times dx. And this here is the change in volume, dV, right? This is the change in volume, the volume on this section here. So therefore, this is equal to minus P gas times dV. So if this moves from, say, a volume VI to a volume VF, then the work done is minus the integral of the pressure of the gas times dV from VI to VF. So that is how we calculate the work in an ideal gas. So now let's look at the sign of this work. So if the work that you do is positive, that means your system is gaining energy, right? Remember that. Positive work equals system gaining energy, right? So this is similar to having a force pushing a box and the box increasing the kinetic energy. So a positive work means the system gains energy. On the other hand, a negative work here means the system is losing energy. For instance, you have a box with some kinetic energy and there is a force that is opposing the motion, so slowing down the box. So therefore the box is losing energy. So negative work equals system losing energy. Okay? So when the work is negative, the system loses energy. When the work is positive, the system gains energy. So now we can apply those ideas to ideal gas processes. What is a process? Well, a process is a change from one state to the other. For instance, a process would be, and let me show you with one simulation. With one simulation, a process would be, for instance, taking the system from this volume to this other volume here. That is a process. Or taking the system from some temperature to a different temperature. That is a process, right? And we represent those processes in a PV diagram, okay? We use PV diagrams to represent processes. For instance, here, there is a process in which the gas goes from an initial volume VI to a final volume VF. So now remember that the work done on the gas is the integral from the initial volume to the final volume of P dV, right? So, and this here, this is the area under this graph here, so this area. So if we calculate this area and take the negative, we get the work done on the gas. So now this is an expansion. You see the volume is increasing, the gas is expanding. And this here is a compression. The volume is decreasing because you're going from this big volume to a small volume. Here we're going from a small volume to a large volume. This is an expansion, this is a compression. During an expansion, the gas is pushing something. So therefore it's losing energy. So during this expansion, the energy of the gas decreases because the gas is pushing something, it's doing work. During a compression, on the other hand, you have to be pushing the gas to compress it. So the gas is gaining energy. Let me show you an example here with the simulation. So during a compression, you're pushing the gas and the gas is gaining energy, right? During an expansion, the gas is pushing something. The gas is expanding and loses energy. And you can see that the temperature increases when I compress the gas because the gas is gaining energy, and decreases when the gas expands because the gas is losing energy. When the gas is compressed, you're doing work on the gas and the gas is gaining energy. When the gas expands, the gas is doing work on something, is pushing something, and is losing energy. So now we know that the work is minus the integral from VI to VF of P dV. And this work is, if it is negative, it means the gas is expanding, is losing energy. If it is positive, it means the gas is uh, compressing and you're putting energy in the gas. So let's see. We have a question here. Take a minute to answer this question. The work done on the gas in this process is one of these choices. Take a minute. Okay, and the answer is minus 4,000 joules. And the reason is, well, you see your initial volume was 2 meter cubes, and then the gas expanded until it got to 4 meter cubes. So therefore, the area under the graph is 4,000, but you have to take the negative because the gas is expanding and is losing energy. Another question here, you have three possible processes, A, B, and C, and they all take the gas from I to F, from initial to final. For which process is the magnitude of the work the largest? For which one of the three processes? Take a minute. And the answer is process A, right? Because the area under this graph here is the greater area. So this area here, this whole thing here, this whole area, that is the work. So now the gas in this area is expanding, right? Well, it doesn't expand here, right? Here you increase the pressure at constant volume, so there's no work done here because the volume is not changing, but then it expands, right, at constant pressure. So here you do work. In this other process, it expands at constant pressure and then the pressure increases at constant volume. So the work done on process C is just this much here, this area here, and the work done on process 8 is the whole area. So to calculate the work in an ideal gas process, we assume the gas is ideal and the process is quasi-static. By that we mean the process is very slow. Show the process on a PV diagram. So you need to plot the process. So you're going to have V and P, and then you're going to have an initial and a final, and then you can plot the process. So the process could be isochoric, isobaric, or isothermal. This is constant volume, constant pressure, or constant temperature. And then once you know all this, well, you calculate the area under the graph, right? You calculate the area under the graph using this integral, and then you check your signs. The work greater than zero means if the work is positive, it means the gas is being compressed and energy is being transferred to the gas. If the work is negative, the gas is expanding and the gas is pushing something, and energy is being transferred from the gas to the environment, and no work is done if the volume is not changing or work is zero. So let's look at an example here. The work done on an expanding gas. How much work is done on this gas, on the gas in the figure? The first thing you have to realize that this is negative because the gas is expanding. It's going from this volume to this volume, right? So we just need to calculate the area and take the negative of that. So the area is, well, the area is this square plus this triangle plus this rectangle. And each one you have the values here, so that gives me 250 joules. And then I need to take the negative of that because the gas is expanding, so that gives me minus 250 joules. Okay.